Fusion power is the generation of energy by nuclear fusion. Fusion reactions are high-energy reactions in which two lighter atomic nuclei fuse to form a heavier nucleus. When they combine, some of the mass is converted into energy in accordance with the formula. This major area of plasma physics research is concerned with harnessing this reaction as a source of large-scale sustainable energy. In large-scale commercial proposals, heat from the fusion reaction is used to operate a steam turbine that drives electrical generators, as in existing fossil fuel and nuclear fission power stations. Many different fusion concepts have come in and out of vogue over the years. The current leading designs are the tokamak and inertial confinement fusion approaches. As of December 2015 update, these technologies are not yet commercially viable. Currently, it takes more energy to initiate and contain a fusion reaction than the energy it produces. Background mechanism: fusion reactions occur when two atomic nuclei come close enough for the strong nuclear force pulling them together to exceed the electrostatic force pushing them apart, fusing them into heavier nuclei. For nuclei lighter than iron 56, the reaction is exothermic, releasing energy. For nuclei heavier than iron 56, it is endothermic, requiring an external source of energy. Hence, nuclei smaller than iron 56 are more likely to fuse, while those heavier than iron 56 are more likely to break apart. To fuse, nuclei must be brought close enough together for the strong force to act, which occurs only at very short distances. The electrostatic force keeping them apart acts over long distances, so a significant amount of kinetic energy is needed to overcome this Coulomb barrier before the reaction can take place. There are several ways of doing this, including speeding up atoms in a particle accelerator, or more commonly, heating them to very high temperatures. Once an atom is heated above its ionization energy, its electrons are stripped away, leaving just the bare nucleus. The result is a hot cloud of ions in the electrons formerly attached to them. This cloud is known as a plasma. Because the charges are separated, plasmas are electrically conductive and magnetically controllable. Many fusion devices take advantage of this to control the particles as they are being heated. Theoretically, any atoms can be fused if enough pressure and temperature are applied, and studies have been made of the conditions required to create fusion conditions for a variety of atoms. Power plants, however, are currently limited to only the lightest elements. Hydrogen is ideal for this purpose because of its small charge, making it the easiest atom to fuse, and producing helium. Cross-section A reactions. Cross-section, denoted sigma, is the measure of how likely a fusion reaction will happen. It is a probability, and it depends on the velocity of the two nuclei when they will strike one another. If the atoms move faster, fusion is more likely. If the atoms hit head-on, fusion is more likely. Cross-sections for many different fusion reactions were measured mainly in the 1970s using particle beams. A beam of ions of material A was fired at material B at different speeds, and the amount of neutrons coming off was measured. Neutrons are a key product of most fusion reactions. In most cases, the nuclei are flying around in a hot cloud, with some distribution of velocities. If the plasma is thermalized, then the distribution looks like a bell curve, or Maxwellian distribution. In this case, it is useful to take the average cross-section over the velocity distribution. This is entered into the volumetric fusion rate, where is the energy made by fusion, per time and volume. N is the number density of species A or B, the particles in the volume, is the cross-section of that reaction, average over all the velocities of the two species. V is the energy released by that fusion reaction. Lawson criterion. This equation shows that energy varies with the temperature, density, speed of collision, and fuel used. This equation was central to John Lawson's analysis of fusion power plants working with a hot plasma. Lawson assumed an energy balance, shown below. Net power equals efficiency *. Net power is the net power for any fusion power plant. Efficiency, how much energy is needed to drive the device and how well it collects power. Fusion is rate of energy generated by the fusion reactions. Radiation is the energy lost as light, leaving the plasma. Conduction is the energy lost, as momentum leaves the plasma. Plasma clouds lose energy through conduction and radiation. Conduction is when ions, electrons or neutrals hit a surface and transfer a portion of their kinetic energy to the atoms of the surface. Radiation is when energy leaves the cloud as light. This can be in the visible, UV, IR or X-ray light. Radiation increases as the temperature rises. To get net power from fusion, you must overcome these losses. Triple product. Density, temperature, time. The Lawson criterion argues that a machine holding in a hot, thermalized and quasi-neutral plasma has to meet basic criteria to overcome the radiation losses, conduction losses and a power plant efficiency of 30%. This became known as the triple product. The plasma density and temperature and how long it is held in. For many years, work has been focused on reaching the highest triple product possible. This emphasis on as a metric of success has hurt other considerations like cost, size, complexity and efficiency. This has led to larger, more complicated and more expensive machines like ITER and NIF. Plasma behavior. Plasma can be made by fully ionizing a gas. Plasma is a fluid which conducts electricity in bulk. It is modeled using magnetohydrodynamics, which is a combination of the Navier-Stokes equations governing fluids and Maxwell's equations governing how magnetic and electric fields behave. Fusion exploits several plasma properties, including self-organization. Plasma conducts electric and magnetic fields. This means that it can self-organize. Its motions can generate fields which can, in turn, self-contain it. Diamagnetic plasma. Plasma can generate its own internal magnetic field. This can reject an externally applied magnetic field, making it diamagnetic. Magnetic mirrors. Plasma can be reflected when it moves from a low to high-density magnetic field. Energy capture. There are several proposals for energy capture. The simplest is using a heat cycle to heat a fluid with fusion reactions. It has been proposed to use the neutrons generated by fusion to regenerate a spent fission fuel. In addition, direct energy conversion has been developed as a method to maintain a voltage using the products of a fusion reaction. This has demonstrated an energy capture efficiency of 48%. Possible approaches. Magnetic confinement. Fusion tokamak. The most well-developed and well-funded approach to fusion energy. As of April 2012, there were an estimated 215 experimental tokamaks either planned, decommissioned or currently operating worldwide. This method races hot plasma around in a magnetically confined ring with an internal current. When completed, ITER will be the world's largest tokamak. Spherical tokamak. A variation on the tokamak with a spherical shape. Stellarator. These are twisted rings of hot plasma. The stellarator attempts to create a natural twist plasma path using external magnets, while tokamaks create those magnetic fields using an internal current. Stellarators were developed by Lyman Spitzer in 1950 and have 4 designs: torsatron, heliotron, heliac and helios. One such example is Wendelstein 7X, a German reactor that is of December 10, 2015 preformed fusion and sustained it for several seconds. Levitated dipole experiment. These use a solid superconducting torus. This is magnetically levitated inside the reactor chamber. The superconductor forms an axisymmetric magnetic field that contains the plasma. The LDX was developed between MIT and Columbia University after 2000 by J. Kesner and Michael E. Mowell. Magnetic mirror developed by Richard F. Post and teams at LLNL in the 1960s. Magnetic mirrors reflected hot plasma back and forth in a line. Variations included the magnetic bottle and the biconicusp. A series of well-funded, large, mirror machines were built by the U.S. government in the 1970s and 1980s. Field reverse configuration. This device traps plasma in a self-organized quasi-stable structure, where the particle motion makes an internal magnetic field which then traps itself. Reversed field pinch. Here the plasma moves inside a ring. It has an internal magnetic field. As you move out from the center of this ring, the magnetic field reverses direction. Inertial confinement. Fusion direct drive. In this technique, lasers directly blast a pellet of fuel. The goal is to start ignition, a fusion chain reaction. Ignition was first suggested by John Nucleus in 1972. Notable direct drive experiments have been conducted at the Laboratory for Laser Energetics, Laser Megajoule and the Gecko 12 facilities. Good implosions require fuel pellets with close to a perfect shape in order to generate a symmetrical inward shock wave and to produce the high-density plasma. Fast ignition. This method uses two laser blasts. The first blast compresses the fusion fuel, while the second high-energy pulse ignites it. Experiments have been conducted at the Laboratory for Laser Energetics using the Omega and Omega EP systems and at the Gecko 12 laser at the Institute for Laser Engineering in Osaka, Japan. In direct drive. In this technique, lasers blasts a structure around the pellet of fuel. This structure is known as a hole ram. As it disintegrates, the pellet is bathed in a more uniform X-ray light, creating better compression. The largest system using this method is the National Ignition Facility. Magneto-inertial fusion or magnetized line or inertial fusion. This combines a laser pulse with a magnetic pinch. The pinch community refers to it as magnetized line or inertial fusion, while the ICF community refers to it as magneto-inertial fusion. Heavy ion beams. There are also proposals to do inertial confinement fusion with ion beams instead of laser beams. The main difference is the mass of the beam has momentum, whereas lasers do not. Magnetic or electric pinches. Z-pinch. This method sends a strong current through the plasma. The current generates a magnetic field that squeezes the plasma to fusion conditions. Pinches were the first method for man-made controlled fusion. Some examples include the dense plasma focus and the Z machine at Sandia National Laboratories. Theta pinch. This method sends a current inside a plasma, in the theta direction. Screw pinch. This method combines a theta and Z pinch for improved stabilization. Inertial electrostatic confinement fusor. This method uses an electric field to heat ions to fusion conditions. The machine typically uses two spherical cages, a cathode inside the anode, inside a vacuum. These machines are not considered a viable approach to net power due to their high conduction and radiation losses. They are simple enough to build that amateurs have fused atoms using them. Polywell. This design attempts to combine magnetic confinement with electrostatic fields, to avoid the conduction losses generated by the cage. Other magnetized target fusion. This method confines hot plasma using a magnetic field and squeezes it using inertia. Examples include LANLFRXL machine, general fusion and the plasma liner experiment. Uncontrolled fusion has been initiated by man, using uncontrolled fission explosions. Early proposals for fusion power included using bombs to initiate reactions. Beam fusion. A beam of high-energy particles can be fired at another beam or target and fusion will occur. This was used in the 1970s and 1980s to study the cross-sections of high-energy fusion reactions. Bubble fusion. This was a supposed fusion reaction that was supposed to occur inside extraordinarily large collapsing gas bubbles, created during acoustic liquid cavitation. This approach was discredited. Cold fusion. This is a hypothetical type of nuclear reaction that would occur at or near room temperature. Cold fusion has gained a reputation as pathological science. Muon-catalyzed fusion. Muons allow atoms to get much closer and thus reduce the kinetic energy required to initiate fusion. Muons require more energy to produce than can be obtained from muon-catalyzed fusion, making this approach impractical for the generation of power. Common tools. Heating gas must be first heated to form a plasma. This then needs to be hot enough to start fusion reactions. A number of heating schemes have been explored. Radio frequency heating. A radio wave is applied to the plasma, causing it to oscillate. This is basically the same concept as a microwave oven. Electrostatic heating. An electric field can do work on charged ions or electrons, heating them. Neutral beam injection. An external source of hydrogen is ionized and accelerated by an electric field to form a charged beam which is shone through a source of neutral hydrogen gas towards the plasma, which itself is ionized and contained in the reactor by a magnetic field. Some of the intermediate hydrogen gas is accelerated towards the plasma by collisions with the charged beam while remaining neutral. This neutral beam is thus unaffected by the magnetic field and so shines through it into the plasma. Once inside the plasma, the neutral beam transmits energy to the plasma by collisions, as a result of which it becomes ionized and thus contained by the magnetic field, thereby both heating and refueling the reactor in one operation. The remainder of the charged beam is diverted by magnetic fields onto cooled beam dumps. Magnetic oscillations measurement. Thomson scattering. Certain wavelengths of light will scatter off a plasma. This light can be detected and used to reconstruct the plasma's behavior. This technique can be used to find its density and temperature. It is common in inertial confinement fusion, tokamaks and fuses. In ICF systems, this can be done by firing a second beam into a gold foil adjacent to the target. This makes X-rays that scatter or traverse the plasma. In tokamaks, this can be done using mirrors and detectors to reflect light across a plane or in a line. Langmuir probe. This is a metal object placed in a plasma. A potential is applied to it, giving it a positive or negative voltage against the surrounding plasma. The metal collects charged particles, drawing a current. As the voltage changes, the current changes. This makes a IV curve. The IV curve can be used to determine the local plasma density, potential and temperature. Geiger counter. Deuterium or tritium fusion produces neutrons. Geiger counters record the rate of neutron production, so they are an essential tool for demonstrating success. Flux loop. A loop of wire is inserted into the magnetic field. As the field passes through the loop, a current is made. The current is measured and used to find the total magnetic flux through that loop. This has been used on the National Compact Stellarator experiment, the Polywell and the LDX machines. X-ray detector. All plasma loses energy by emitting light. This covers the whole spectrum, visible, IR, UV, and X-rays. This occurs anytime a particle changes speed, for any reason. If the reason is deflection by a magnetic field, the radiation is cyclotron radiation at low speeds and synchrotron radiation at high speeds. If the reason is deflection by another particle, plasma radiates X-rays, known as Bremsstrahlung radiation. X-rays are termed in both hard and soft based on their energy. Power production. Steam turbines. It has been proposed that steam turbines be used to convert the heat from the fusion chamber into electricity. The heat is transferred into a working fluid that turns into steam, driving electric generators. Neutron blankets. Deuterium and tritium fusion generates neutrons. This varies by technique. It has been proposed to use these neutrons as a way to regenerate spent fission fuel or as a way to breed tritium from a liquid lithium blanket. Direct conversion. This is a method where the kinetic energy of a particle is converted into voltage. It was first suggested by Richard F. Post in conjunction with magnetic mirrors, in the late 60s. It has also been suggested for field reverse configurations. The process takes the plasma, expands it, and converts a large fraction of the random energy of the fusion products into directed motion. The particles are then collected on electrodes at various large electrical potentials. This method has demonstrated an experimental efficiency of 48%.